non-ferromagnesian silicates. So the non-ferromagnesian silicates do not have iron and magnesium. Since they don't have iron and magnesium, they are light in color. So for example, they're usually pinks, whites, and tans. And kind of any like very, very light gray, things like that. So they're very light in color. They're also, because they don't have the iron and magnesium, they are less dense. So they range from 2.6 to 2.9 grams per centimeter cubed. And they make up the continental crust. So remember from plate tectonics, continental crust is less dense than oceanic crust, and it's because they're made up of primarily non-ferromagnesium silicates. Remember, silicates are the most common type of minerals. So most of the minerals on the Earth's surface and throughout the Earth are silicates. So there's several different groups. And so the first group we're going to talk about is the feldspar group. Okay, so the feldspar group is generally white, pink, and gray, and they range in that spectrum. They have two cleavage planes. The two cleavage planes are at 90 degrees. Couldn't find my @ symbol. And they're framework silicates. So these have the most silica because they are the most complicated silicate structure. All the oxygens in the silicate tetrahedron are bonded with another tetrahedron. So they have the highest concentration of silica and oxygen. They're common in igneous rocks. So there's two different subgroups of the feldspar group, and the first one we're going to talk about is the potassium feldspar group, which is also known as K-spar. Potassium is the element K, so K-spar, potassium, feldspar. So it's the potassium feldspar group. Generally, they're light in color. They're pinks, whites, and tans. Potassium feldspar in particular is primarily pink, but you can see it in white as well. But they have something known as laminae. Lamellae, sorry. The laminae are these little vein-looking things on the surface. So you can see it looks like they have veins. Those are your lamellae. So you can see these right here. It just looks like if you trace them. This one too. So that's a good way to tell the difference between potassium feldspar and plagioclase feldspar, which we're going to talk about next. Because they have the same hardness, which a hardness is 6. They have two cleavage planes. Plagioclase won't be pink, but both potassium feldspar and plagioclase can be white. So the lamellae is unique to the potassium feldspar group. Plagioclase, which is also in the feldspar group, got some letters there. The plagioclase group, once again, it primarily has sodium and calcium instead of potassium, so that's why its colors are a little bit different. But like I said, it's a framework silicate. It has all the same properties as the potassium feldspar because that's what makes them a feldspar, but they have something known as striations. Striations are grooves on the surface. So if you look here, this is reflecting. Usually you have to look at it with the light reflecting off of it, but you can see how there's parallel lines that look like they're grooved on the surface. Those are the striations. So they're just parallel lines grooved on the surface. And when you get to the minerals lab, you'll see lamellae and striations, and that's the easy way to tell the difference between them. And you can see them here. They're parallel. Well, the laminae look more like veins. They're not always parallel and perfectly straight. Okay, so the next group is quartz. So quartz is only silicon and oxygen. It has a chemical formula, SiO2. So it's only silicon and oxygen, so it has the highest concentration of silicon and oxygen. It's a framework silicate. Has a very complicated structure. All the oxygen are bonded with other tetrahedra. And since all the other oxygen are bonded and there's no other ions because it's only SiO2, it has fracture and not cleavage. Which fracture means that there's no planes of weakness, so it just breaks randomly, and so the surface looks very, very bumpy. So this right here, the one in the front, is a crystal form, makes prisms, but the two in the back are not in crystal form, they're just massive, and they have bumps on their surface. So they have fracture and not cleavage. There's a wide variety of kinds or varieties of quartz and kinds of quartz based on impurities. Quartz takes in a lot of impurities, and these impurities are what determine its color. Like you have rose quartz, smoky quartz, clear quartz, amethyst. Huge variety of quartz. Quartz can come in almost any color, blue, green, yellow, just because of the impurities it takes in. So it has many different colors, which all have their own name, and so those are known as the varieties of quartz. The next one is part of the mica group, which I talked about already, so I'm not going to go over the properties, but this has the same properties as the mica group in the ferromagnesian. However, it's light colored. It doesn't have iron and magnesium, so it's light colored because it has a lot of aluminum in it. But as the one plane of cleavage, which you can see here, this is a sheet that's been peeled off. Muscovite is the most common type of non-ferromagnesium mica, but lepidolite, and there's some other ones, but muscovite is really the only one you'll see. It's a very common igneous and metamorphic mineral. And then finally, we have clay minerals. So these are sheet-like silicates, so they're very similar to the mica group, but they're slightly different because they're sheet-like. They're not fully sheets. And they result from weathering. So when we get to sedimentary rocks and weathering, we'll talk more about clay minerals. They're very hard to tell apart without using something known as X-ray diffraction. So usually they're greasy, they kind of look like clay. And the common example is kaolinite, which is shown here. This is just kaolinite, but they all look very, very similar.